So we've now got the idea of finding the exact solution, and this is going to, of course, be particular to the Burger's equation. The problem with all these exact solution methods is they're not very general. Show how great that colour is. Let's try something a bit more fancy. All right. So remember, we can solve this numerically with our split-step spectral method very easily. We could got this travelling wave solution, but we're going to find an analytic solution. It'll make you feel great that you found it and clever, but it's not necessarily any better than the solution that we had, by numeric, any easier to use in the numerical solution. Okay, so we write this equation as the following. I've already done this. It's sort of in conservation form, if you like. Remember how we used to do this thing here? It tells us that integral from minus infinity to infinity of this will be 0, so u must be, the integral from minus infinity to infinity of u must be conserved. So what we do is the following. I'm going to change colour here. I sort of believe the colours make a huge difference. Everyone's learning. Sure how true that is. Okay, we're going to find a function psi that satisfies this equation here. The x derivative of psi is u, and the time derivative of psi is equal to u. Essentially, once you've found one solution of one equation, you can transform and find the solution to other equations, by differentiating or manipulating it. So solutions sort of appear in families. Entirely obvious why we do this, but we know that the u dt is d by dt of u is equal to d by dt of d by dx of psi, which is equal to d by dx d by dt of psi, which is equal to d by dx of nu dx u minus u squared over 2. So if we can find this function that satisfies those two equations, then we're going to solve this equation for u. So now we know, since dx dt is equal to u, we can substitute that in here. So our equation we want to solve for psi as dt psi is equal to u nu dx squared psi from here minus a half dx psi squared. So if you look at it, we've got a little colour around it here. This equation here, it's hard to draw straight lines with this pad, and this equation here, these are the two. We've transformed from that equation to that equation. It's not a huge advance, is it? It doesn't seem to be made very much difference. It is slightly different, but only slightly different. We have the dx of u squared, and now we've got the derivative inside the, right? That's the only change, right? dt is equal to, that's the same. This plus has somehow become, we've changed sign. So, no, we haven't, because this would go over here and become plus. So this is exactly the same. We've just transformed this part from being a u squared with an x derivative to being the x derivative squared. All right. So it doesn't seem to have made a heck of a lot of progress at this point. So let's just write that equation out again. Okay, I'm trying to avoid this yellow. I reckon it's not easy to see. I'm going to do it in purple. So this equation is dt psi is equal to nu dx squared psi minus a half dx psi squared. And then we go and introduce this transformation. This equation, someone has studied this equation before. And what this equation is going to linearize this equation. Okay, so this is not at all obvious what is going to happen here, but a miracle is going to happen. Let's see how that works. So the x derivative of psi is equal to minus 2 nu x derivative of psi over 5. And then the x derivative squared, now we've got to differentiate this. So what do? We use the quotient rule. Or we can just differentiate the top and do the product rules, maybe easier. Minus 2 nu the x squared psi over psi plus, okay, now we're going to differentiate this to the minus 1, which is going to give us 2 nu, but the minus power of minus cancels with the minus, we get dx phi squared divided by phi squared. And then we're going to go the time derivative of psi is equal to, it's going to be minus 2 nu dt psi over phi. Okay, so what we've got, then we substitute all of these things, let's change colour. Right, we've got 1, 2, and 3, and we substitute them into this equation here. And a crazy sort of miracle happens, because this extra term here, dx psi squared, half that, exactly cancels with this term from here. Okay? So we end up doing a whole lot of crazy cancellations happen, and we end up with this equation here. dt, I'm not going to go through all the details of that, but you can sort of believe that this is possible if you add them up. Okay, dt phi is equal to that, and then you've got this nu dx squared, multiply that by nu, minus this term here, which is that squared, which cancels that off, and then you can rearrange it and end up with this equation here. So, of course, this is the heat equation, and we can solve that. The problem is that, let's just think about this piece of genius. We've now worked out that we can solve exactly this equation, so we've got to, unfortunately, that tells us phi, then we can, from phi, we can work out psi, and then finally from psi we can go back to u. So we're a long way from the solution, and the initial condition was given is a long way from phi, so we've got to convert the initial conditions. I'm going to stop at that point and then we'll start again.